Hello everyone, and welcome to this basic introduction of SN2 reactions. So we've already talked about acid and base reactions, and so to build up in complexity, the next step is going to be SN2 reactions, where there's a lot of things that are the same, but there's going to be a few differences. So to get started, let's look at our first SN2 example. This is a reaction that I've shown here at the top. As you can see, it's OH minus, and then this ethyl chloride is going to turn into this ethanol and chloride minus. So what's changing in this reaction? Right? Obviously, there's a switch happening, right? The chlorine is being switched for the OH, and then the OH is being switched for the chlorine on the product side. So when you see that happen, that's what makes this reaction a substitution reaction. Basically, it just means you're substituting one thing for another. So that's the S of the SN2 reaction. So while we're here, let's talk about the other two parts of the name. The N stands for nucleophilic. Nucleophilic is about nucleophiles, right? Which we've talked about a little bit. Nucleophiles have electrons and they like to make new bonds and things like that. So the nucleophile here is the driver of this reaction. It's based on how good your nucleophile is. It's going to determine how well the reaction goes. So that's why it's nucleophilic. If the electrophile was the thing driving the reaction, it'd be called electrophilic. And we'll see some of those later on. The last thing that says is this 2. The 2 stands for bimolecular. The bimolecular has to do with the kinetics of this reaction. So kinetics are how fast a reaction goes. They're not really based on the stability like the KEQ or things like that would be. They're just based on how quickly something happens. The kinetics can also be measured by changing the concentrations of products and seeing how that affects the rate of the reaction. So that's where it came from. For a bimolecular reaction, what that means is that in the slow step of the reaction, there are 2 molecules coming together. That's one of the key steps. And what we're going to see is the key step in this is going to be a part where there's 2 different molecules coming together. So an important part of this reaction is going to be its mechanism. So let's talk about that next. So remember, whenever we were talking about a mechanism, it's nice to have the products here. So generally, if I'm going to ask you a mechanism question, I'm always going to show you the products from now on. The acid-base ones you can kind of predict, but from now on, if anytime we have a mechanism question, I'm going to show you what the products are. For the acid-base questions, I did ask you to predict those products, but that's because a Bronsted acid-base is hopefully easy to figure out the products. For these, as we get more complicated, that's going to be a little bit harder, so I want to make sure that I'm grading you on only the mechanism if that's the question I'm asking. So from everything in section 2 and beyond, we're going to actually not have to draw the products anymore, okay? So if I'm looking at this one, I've already got the products shown, so the next step would be to identify the nucleophile and electrophile. We're going to do it the same way we did before, it's just they won't always be a base and an acid. But what we learned about nucleophiles is still true. Nucleophiles tend to have a negative charge or have a lone pair, and then electrophiles tend to have either a positive charge or a partial positive charge. So we can use that to identify these. So looking at this reaction on the reactant side, which one of these would be the nucleophile? Right? It's going to be the OH minus because it has a minus charge. So let's label that. If that's the nucleophile, that means the other piece has to be the electrophile, so we'll label that. And then the next thing that we're going to do is to start drawing the curved arrows. Now remember we said that anytime you have 2 atoms coming together, so an arrow like this where one of them has the lone pair usually, and then draws to another atom, that's going to make a bond. And anytime you have arrows from a bond, that's actually breaking a bond, so like this example. So that's what we're going to use our arrows to do. So if you look at our products, what is the new bond that we're making? Right, it's going to be this carbon-oxygen bond, so I'll highlight that, and that's going to make a new bond. So how would I draw that arrow? It's going to start from the O, because that's where the electrons are. There's a lone pair there, and it's going to go to which carbon? Right, the carbon that's next to the chlorine. So we're going to put that there. The reason that it's going to attack there is because you have a polar bond, and that's a partial positive. So if you look there between the carbon and the chlorine, that's going to have a partial positive on this side and a partial negative on this side. So we said that electrophiles like to have a partial positive, and that's why the O minus is attracted to that spot. But also you can tell by looking at the product, the oxygen had to attach to that carbon to get the product. And then the chlorine's going to have to do something. So what happens to the chlorine over on the right? It's broken off, right? So that means we're going to have an arrow from the bond to the chlorine to break that off. And if you look, this is almost identical to the mechanism for Bronsted acid and base, except for it's attacking a carbon instead of attacking a hydrogen. For these particular reactions, the nucleophiles can vary, and I'll show you some examples, but the electrophile tends to be pretty similar in that it's always going to have some sort of structure of carbon, so that's going to be the R group, and then it's going to have a leaving group. So for this reaction, the leaving group would be the chlorine because that's the piece that leaves, and we'll talk more about that later. All right, so now that we sort of got an idea, let's look at another example. All right, so here's another example. As you notice, something's different. In this case, we have something that's above the arrow instead of having two things on the left. Anything above the arrow in organic chemistry is still a reactant. It's just called a reagent. The difference is the things over the arrow are things that you can generally buy. They tend to be things that are mostly inorganic or not organic. The majority of the structure tends to be the thing on the left. So on top of the arrow, that's called the reagent. And then the thing on the left is called the starting materials, but they're both reactants. All right, so let's see, first of all, let's try to predict what we think the product's going to be. This type of question, where basically I've left part of the reaction out, we're going to refer to as a box question later on because normally in a normal semester you draw your answer in the box. But for presentations, it looks weird to draw it in the box. I never draw it the right size, so we'll just put question mark for now. So for right now, what we're asking is what organic molecule goes where the question mark is for this reaction. We have a leaving group and we have a nucleophile and they're going to switch places. So draw what you think that would look like. Pause the video if you need to. Is this what you got? Hopefully it was, but if not, that's okay. Let's look at the mechanism to look a little closer. So again, we want to identify our nucleophile and electrophile. This will be one of the easier examples. So as you can see, we said last time that electrophiles in SN2 reactions have carbons and leaving groups. Which one has something that looks like it's got a few carbons and then also looks like it has a good leaving group? Something that's like chlorine is my hint. Right, it's going to be this one here. So let's label that as the electrophile. Then that means the other thing is the nucleophile right here. Now, the nucleophile has this sodium on it. What's that sodium doing? The purpose of the metal is actually just as a counterion. So what this actually is C minus with an N on it, and that's the nucleophile part. So before we just didn't show that there was a sodium probably on the hydroxide, we didn't show the counterion. But when you buy it at the store, it's always going to be balanced, so the reagent version is what you're going to see the most often. When you're doing the mechanism, you want to redraw that without the metal, otherwise you have to show where that metal goes, and that would be more arrows and not what we want to do. It just makes it more complicated. So you just redraw it with the minus charge where the metal was. So now for the mechanism, my next step is going to be drawing the arrows, right? So my arrow is going to start with my nucleophile, so that'd be right here. I can just do it on the minus charge, or you can draw a lone pair. And then where is it going to want to go on that electrophile? Well, if we look back before, it went to the carbon that was attached to the leaving group. So for this one, if I have carbons 1, 2, 3, which carbon would that be? Right, it's going to be carbon 2. So let's attack carbon 2, and then break that bond, and then that should give us the product. Notice that for this problem, I did not show the Br minus that left after it left. You can show that if you want to, like this. We can go ahead and balance the equation so that we show the Br minus and the sodium plus. The difference is for organic, we normally don't do that. We actually don't show anything but the part that's related to the carbons. So I can actually cross those out and just call them byproducts. Those are things that we aren't trying to get. They're not what we want, and they would actually be washed out if we did an extraction, which is what people normally do at the end of a reaction. So we just don't have to draw them. You're always welcome to draw them. I would never count out for that. But also don't depend on me drawing those because usually I'm not going to draw the byproducts because that's just not what you're going to see in the future for your work. So we'll stay consistent with what you would see in a textbook or future classes. And in that case, the only product you would draw, if asked, was this one. So if you remember, I only had one question mark there. That's because there's only one major product, and that would be that organic product. So that's what you would have to draw on a quiz or exam. And if it's on paper, that would go in the box that I would provide. So before we move on, I want to point out that the two examples we've seen so far are a type that we are going to call strong nucleophile. A strong nucleophile has a negative charge on the nucleophile. It's either shown with a minus charge, like the very first example, or it's going to mostly be shown like example 2 here, where it's got a metal. So anytime you see a nucleophile that has a negative charge, or it's covered up with a metal, that's going to be a strong nucleophile. Anytime you see that as well, you're going to have a mechanism like we just saw. It's only going to have one step. So there's just one thing that's happening. There's two arrows, but there's one thing that's happening at a time, and it all happens at once, and then you get the product. So that's a strong nucleophile. In contrast, we can have one other type of nucleophile, so I'm going to show you an example of that now. So one type we can have is strong nucleophile. The other type we can have is called a weak nucleophile. For the weak nucleophile type, your nucleophile is not going to have a charge. Instead, it's going to have an extra hydrogen that after attacking can be removed. So if we look at example 3, let's try to identify the electrophile and nucleophile. Remember, the electrophile will have a leaving group, so which one is that? Right, it's going to be this one on the left, the starting material. For that means the nucleophile has to be the water. Now, as you can see, water doesn't have a charge, but what it does have is lone pairs, and we know that nucleophiles either have a negative charge or a lone pair, so that makes sense too. So let's look at our mechanism and see what would happen. This mechanism actually happens in 2 steps, but the first step is going to be the same. The nucleophile is going to attack the electrophile, so let's look at that. Our nucleophile is going to start from the lone pair, so that's going to be the start of our arrow. And where does it want to go on the electrophile? Right, it wants to go to the carbon that has the leaving group. So let's draw that. And then that's going to have one more arrow, so what do we need? Right, we need the arrow that breaks the bond between the carbon and the bromine, so let's draw that. And then that will be the first part of our mechanism. Now, if we draw what that would make, it actually doesn't make the product. If you look on the right side, there's an OH without an extra H on there. So what's going to happen? Let's draw the intermediate, is what it's called, the thing that the arrows would make that's not the final product. So we'll draw that. So first I'm going to draw a straight arrow to show that it's a different step, and then I'm going to draw the product. So I'm going to draw the first 3 carbons, so 1, 2, 3, like that, and then I'm going to attach an O to carbon 3, like I did, and then what's still attached to that O is 2 hydrogens, so I need to draw those. Now I know I'm going to have to take off one of the hydrogens, so I'm going to draw one of them just normal, and then one of them I'm going to show the bond, because I know I'm going to have to break that bond. So I'm going to draw it like this. So now I've got all the correct bonds, but I want to double check the charges. If I look here, my arrows went to the bromine, so that would actually mean I'm making a bromine minus. That's a byproduct, but you could draw it on the side if you want to. And then if I have a minus, I know I'm going to have a plus somewhere. So where would my plus be? It's going to be on this structure that I've drawn, but it's going to be on the oxygen. Notice when in my curved arrows, the arrows went away from the oxygen. That's one way I can tell there should be a positive there. The other way is because oxygen has 3 bonds, and oxygen with 3 bonds is always going to be a positive formal charge. All right, so now I have to figure out how I'm going to get from the structure I've drawn to my final product. If you look at that, those are just an acid and its conjugate base. So we're just going to do an acid-base reaction. So I know that's going to be my last step, so I'll go ahead and draw my arrow. And then my curved arrow is going to be something coming to get the proton from that acid. So what is in my solution that could act like a base? I actually have 2 choices. I have a Br minus and I have water, and both of those could act like a base. So when I'm trying to decide which would be the better base, I'm going to look at the pKa's of those and try to figure that out. So if I look at water, the pKa of water for H3O plus is the opposite. That's going to be negative 1.5. And then if I look at bromine, that's like, I think, negative 9 or something like that. So that's going to be a lot less likely to form. So I'm actually going to use water. So I'll just draw another molecule of water. Anytime you see a reagent, assume you have an infinite amount of that because there's always more. So we'll draw the water, and that's going to be my base / nucleophile. Then my arrow is going to go from the lone pair to the hydrogen, and then I'm going to break that bond to go to the oxygen, and then that's going to be my acid-base reaction. So hopefully that looks familiar because that's just review from our last section. So as I said before, the weak nucleophile type is going to be a little bit different. The main difference is that the mechanism for this type of reaction has 2 steps, whereas the previous one just had one thing happening, right? So for the other one, we just had the SN2 reaction part, which was the very first step of this one. But this one has an SN2 part, that's the first part, and then the second step would be the acid-base reaction part. So that's this one right here. And again, the other difference is the nucleophile. And that's going to determine how we draw the product. For the first type, you just took the nucleophile and switched it with the leaving group. In this case, you have to take off the leaving group, add the nucleophile, but then you also have to remove the extra hydrogen. So you have to take that off as well. So with that, I'm going to end this video about SN2 basics. Something else that we can talk about later is backside attack, which has to do with the transition state of this reaction. And also the different types of nucleophiles are listed on the activity on Blackboard. So you can see that it's called SN2 reaction list and mechanism practice. So you can see the different types there, and we can talk about those later. I hope you have a great day. Thanks for watching.